welcome. Thanks for coming. I want to start out. One of the things I want to say is that through this presentation, that I'm aware that there are ways that we can do tree segmentation, delineation, and classification at small scales. Like we can go in and by hand do that. We can look at air photos and some lidar and draw lines around things. This process is to do it at scale. The idea is to do it at a county scale. So how can we go through this, automate this, so we can run through a tree class identification and classification scheme and do it at a large area. So we're not spending a lot of time, we're not using a lot of our resources. Why county scale? Because that's the unit that we tend to collect our lidar in. So I'm having said that, one of my worries in this sort of work is that I'm going to do it and then I'm going to open up probably LinkedIn and see the next day that one of Matt's friends has published a new way to do this that is going to completely antiquate what was 6 months worth of work. And so if you have ideas, if there are other things that you see that might be useful to this process, I'm really open to ideas because this is a bit of me just chasing a rabbit and trying to catch it. So tree detection and classification using multiple remote sources. So what's the first step? Is get yourself some high resolution data. And in this case, this is the Milwaukee County 2020 lidar. Why the 2020? Because the 2025 is not done yet. I asked Zach this a couple weeks ago and he gave me the reasons answer. So having said that, there are some things that will change with the 2025 release and potentially with the potential to expand this to the entire 7-county sewer pack region. So you guys are probably familiar with lidar data. This is a presentation that I did a smaller version of for a more lay audience. But the key point here, I just pulled out the identify pop-up from ARC. And you get with the lidar, you get 3 really key pieces of information. You get the elevation of that point. You get the intensity, how strong was the return for that point. And then what's else? Oh, you get the coordinates for the points, the X, Y. So you get X, Y, Z, and how strong was the return. So the second step is we don't care about all those points. We just want the tree vegetation points. So filter them out, right? There's a classification that was done that AIRS does or I think AIRS did this one. The contractor will run a classification model, classify those points into bare ground, structure, tree, or it's low, medium, high veg. They have transmission lines, transmission towers, bridges, a number of classifications that are standard across the LAS files. So I filter those out. So all we're looking for is the medium and high vegetation. So you'll notice around some of the edges here though, you'll see that those aren't trees. That's going to be a problem that I'll tell you about later, but ignore that for now. Just there. So the really crucial step here is to pull out. So when we look at those points, it's just a bunch of points, but we have this dimensional component to it where we have the elevation. And what we want to do is we want to take those points and turn them into discrete trees, not just a canopy. We want to get discrete trees. This is called segmentation in the process. So I'll give you see if this actually works here. Oh, the mouse is not connected to my computer, just by the way. Sorry, so I didn't want to run live. I didn't want to run into the problems that the last guy had. So I recorded this, and what you can see is as you zoom out, you pan in the ARC 3D viewer. Esri has a little extra flavor that they do a segmentation on there to pull those out that you can do on smaller scales. But what I'd like to say, even at these small scales, you can see these points, and our brains automatically say that's the edge of the tree. Those are a bunch of points, and there's the edge of a tree. This is what, it's amazing the amount of work that it takes to train a computer to do something that our brains do in a half a second. Like we know what trees are, we recognize them, we recognize the shape, we can do them. So it's trying to give the computer the information that says, this is what a tree is, this is what the edge of it is, this is what the shape looks like, so you have to give it training data points. You have to give it a structure to say, this is how we're going to identify it. So yeah, I'd just like to zoom me around, it's kind of fun. Except that your computer gets really hot, and then your cat comes down and lays on your computer because the computer's really hot, and the computer doesn't cool off and it shuts down. Anyway, so we filtered out those structures now. The next point, so I used the lidar package, which is in R, and why R stats? Because 2 reasons. That's my native language for programming, and number 2, I'm a state employee. It's really hard to do stuff on your computers in other languages because you have to go through IT and get stuff approved. Python can be really clunky. Kind of runs into all sorts of issues. You don't have that with R. Our packages are typically just text files, so so it's easy to use and it's powerful. It is actually quite fast. That is my preferred platform. But so the lidar package, the way it was written, is that what it does is it takes the canopy height model and it uses a focal window based on what you define. In this case, it's the height of the tree is for Wisconsin is the best allometric equation to say the height of the tree is typically the diameter of the canopy. So you say the way the lidar package typically works is it runs a maximal focal window and it goes around and it looks at that canopy surface. I'm going to go in here. And it looks at the top of that canopy and says, here's the local high point. Oh, here's the next local high point. Here's the next local high point. It says those are tree stems. That didn't work. And it doesn't work in Wisconsin because Wisconsin deciduous trees work for two reasons. Wisconsin deciduous trees don't tend to have that real distinct curve to them. A lot of our trees have a kind of a flat top. Like honey locust especially might have 4 or 5 highest points on the top of it. Works well for coniferous trees that are pointy, but for other things it doesn't work that well. Second reason is almost all of our lidar is flown leaf off, which takes that canopy structure and makes it a lot more diffuse. So what I did is I actually, through emailing back and forth with the author of that package, I shifted the model so the maximal focal window doesn't rely on height, it relies on the density. So each one of these trees now is symbolized by the density of it, red being the darkest. Because the density, you're getting the densest point of returns, like how many times did it bounce off that tree trunk, and that tends to be the center of the tree, or the trunk of the tree. So I used that and it worked great. And so that process, next step is to identify that individual point of the center of the tree. And then from there, we need to draw that ball around the tree. How do we go about doing that? And that's where we go back to the canopy height model. That canopy height model basically runs a convex hull over the top, and the effectively works is, runs the differential equation. It's a differential equation because non-continuous, so that says that's the edge, or if it goes to 0, that's the edge. So you end up with the delineation that draws a polygon around each one of those trees, which is what we get. So we get a nice structure, or we get two nice feature classes out of here. We get points of the individual trees, and then we get the polygon with the individual trees. So that's step one. We've identified all our trees. Now we can do this at a county level, and we can say, this is how many trees Milwaukee County has. And that's great. That's actually a lot more than you could do before this, and that's important for a good number of reasons. And that's also going to come along with some statistics like the average height of that tree, the maximum height of that tree, the diameter circumference, so we can start calculating some volumes of vegetation, things like that. But what's really interesting is if we can identify the species of the tree. Then that tells us what is the composition of our urban canopy. So what we do with that is we go back and we take the polygons and I'm going to step aside for a second. One note on my process in this is I did all of the coding and learning how to do this on my local, on this guy right here. But I would do it on like 4 LAS tiles at a time. Then when I got to a spot that I knew something would work, we have a remote machine, so in the Rhinelander, I remote desktop into that. That one's great, it has 512 gig of RAM, I think 32 cores, something like that. So I put it on there, and then I have that machine do the heavy lifting. So I let it run there, and I tell anybody if you hear it smoking or you smell it smoking, then give me a call, or actually don't. Pretend it wasn't me. If it was smoking, there won't be any paper or breadcrumbs back to me. But anyway, so I upload this to the big machine, and then go and take all those polygons, and we extract a whole bunch of different data from that to get features of those polygons. Like I said, we have the intensity, we have the density, we have some height information. And so we go through, I'm not going to go through every one of these except to point out that we got it from a number of sources and a number of different resolutions. So I used, in R, I used the R package, Terra, to extract these underlying values of layers that I downloaded from NAIP, WROC. I got the RGB from both of those, and then the near infrared from the NAIP imagery. And NAIP is, 18 inches. WROC from Milwaukee County, and this one I think was 3 inch, so I resampled that to match the NAIP, so it's the same extraction grid cell. We got the Milwaukee County data that I mentioned. So then I went to Google Earth Engine, and I used Google Earth Engine to extract for Milwaukee County a grid that's 10 to 20 meters of the, there are three spectral bands, and I think there's 3 NIR bands. There's a couple red edge bands in there. So these are all the bands that are kind of relevant to vegetation. So I pulled those out, and then this is a key one. This is a special one that we have in Wisconsin that not a lot of other states have, is we have an urban tree inventory. So the cities maintain inventories of their urban street trees that has various information, the height, the class, the height, the diameter, the location of it, but then they also have species in there. So we have this training data set, which is really valuable. I'm gonna spend a little bit of time on that in just a minute. But then I also do some calculations. We calculate out NDVI and NDWI. Some of the other ones I used from Sentinel was I tried to capture the green up period because that's a known, in the phenology of trees, different trees leaf out at different times. Like my sugar maple on my property leaves out like right as soon as it gets warm. The black walnut's like, it's not May yet, and we'll start in May. So there's different windows of phenology. So that's just useful as a point. I picked up when the EVI, NDVI, and NDVRE, it's the red edge NDVI basically, when those hit 50% of their yearly maximum, they hit 80% of their yearly maximum. And that's from the literature, is about that window of where you're really getting the green up period, and that transition from 50 to 80 is typically pretty short. We're looking at maybe 1 to 2 weeks. So I calculate those dates, and then I calculated the duration, because some trees also take a long time to leaf out. My sugar maple takes its time. It starts quite early, but it takes a while to leaf out. Black walnut starts to leaf out, and like 4 days later, it's completely leafed out. So that's a known thing that we have with the trees. So we're just trying to give more information to the model to say, this is how you identify these individual species, is based on these reflectances and these calculations. So at the inventory data, then for Milwaukee County, we have 200,000 points, which is a lot of data. So that's a solid training and test data set. One big problem, though, is if you notice the Acer PL up there, that's Norway maple plantonoides. I think I'm pronouncing that right. But we have 65,000 Norway maples in Milwaukee County. So we create this really unbalanced training and test data set, which is really problematic. And then you go down the list, you see the next two are ash species, Fraxinus, and then Gladitzia, which is a fun word to say. Gladitzia robinia is black locust, or honey locust, which is most of those. But those 3 species comprise like almost half of the entire training and test data set. So what happens when you run a random forest model, that's the little picture down here. I always think of it like upside down Plinko. You know how you start with Plinko and it like goes down? This is one where it goes the other way, where you start out at the top and then it's trying to narrow it down into the bin that it could be. But so we're taking those reflectances and we run the random forest model, and it picks it out at the end, and it gives a probability of what it is at the end. It started out at the beginning just giving it the species. That did not work at all. What the model said is that, yeah, everything's Norway maple, because there's 65,000 of those in the training data set, so everything's a Norway maple. Or I tried to filter it out a little bit, like then it became, okay, everything's a maple or an ash. That's it, we don't know anything else. So I stepped back, and what I ended up doing is I did a stepwise or a hierarchical random forest modeling process, where I started out at the beginning of the two, tried to split them into the 2 cleanest categories, which was deciduous versus evergreen. Like, do you lose your leaves or don't you lose your leaves? So I started out with that, and then the outcome at the end of that is a probability that you're deciduous and a probability that you're evergreen. I take that, so going back to here, so I've got this long list of attributes. I tack the results of that on and call that another attribute of that tree, that it's got a probability of being deciduous and it's got a probability of being evergreen. And then I say, well, are you coniferous or broadleaf? Do you have or needle leaf or broadleaf? And take that, pipe that on as a probability for each one of those. And I said, are you simple, compound, or needle leaf? Pipe that on at the end. And then I worked through this process in a number of ways, and then I figured out the best way to go about doing it was just to step down this list to say, okay, so now we're gonna say, are you a Norway maple or are you not a Norway maple? So the model's gonna look at it and say, well, it's got an 85% probability of being a coniferous tree and being evergreen. So the model's gonna learn really quickly that from the training data, that's not likely a Norway maple. So then you're gonna get a probability of Norway maple. And then step down the list of each of those. I got down to Caricis, which is oak trees. Or Caracus, my friend Dan. I don't know if you know Dan Buckler. Great guy, but we're out in the field one day and I pronounced the Latin word wrong and I said, oh, that's how it's pronounced? He said, yeah, well, I had Latin in college. Like, oh. So now every time I say a Latin word, I say, oh, wait, Dan, you had Latin in college, right? So then I raised my finger. But so I went down to Caracus, and below that, the number of species were too small for the model to really do well with it. I kept getting model results that were not satisfactory. So I just broadly grouped them in. So like if you were, I don't know, if you're a birch tree, you become broadleaf deciduous. Like you're broadleaf deciduous, just like if you were, I don't know, something, little hackberries in there. Yeah, hackberries, Celtis, that's one of the ones that's in there. But you're just in this general group of generic deciduous broadleaf trees. So at the end of the day, what I get out of this is I get polygons that have the predicted tree species. So when I'm doing the training, when I'm training the model, is I hold out, I think I did 70-30 on this one, so 30% of the training data points are held out, and then I go back and I test those points, and I say, did it get it right? You know, point out a couple of them here, like it does really well, where the bold is the predicted, the light, no, other way around. The light one is the predicted, the dark one is the actual. Like here, those ones match up. So we hit on the Acer plant Nodes a whole bunch. We missed up there. It's actually a hackberry. Called it Norway maple. It was wrong. Down here, we got hackberry right. There we got, it was a hackberry. The model called it an elm. So we go through that process and measure the accuracies of each one of these, of the species or generic groups of genera. So at the end of the day, the take-home message is this model does coniferous versus deciduous really, really well. Like that's a no-brainer. And it's go back real quick. I'll show you one in here. I subtracted these two. Okay, the difference between the red, green, and blue. The difference between leaf on and leaf off in the WROC and the NAIP. That's like that was it. Like I can model coniferous versus deciduous just on those two variables. So it did really well with that. And the nice thing about that is it can cut those out of the model, put those with a high probability in that bin, and then you're not likely to get those wrong. It's not likely to confuse those with something else going down the list of modeling. What it can't do is differentiate a spruce from a pine. Like there's just, and you look at the reflectances. So when you take these, our training polygons, and you look at the summary reflectances across the species, spruce and pine from the air and their reflectances do not look very different at all. There's not a lot of phenological changes that happen either with them. Those is going to be trickier, especially in Wisconsin. One issue, this is kind of a strange issue, where a lot of the work that's done out west or in the mountains is often more successful because of where mountains are more arid environments, is because the tree canopies are far less dense than they are here. And two, water is such a big differentiator between different species and how they use water because they're water short. So trees will look a lot different from above. Colorado blue spruce, first time I went to Colorado, I didn't know why it was called the Colorado blue spruce. And you go to Colorado and you go, oh crap, they're actually blue. Like they're blue. And it's because of the water and soil conditions. So yeah, so here we have the contrast between different species is much different here. And you notice if you get down to the bottom of the list with just generic maple, right? Generic maple looks like everything. Like if you were to draw do a principal component analysis and put all the tree species around there, maple would be right in the middle of everything and overlap everything. So everything just kind of looks a little like a maple, and a maple looks kind of a little like everything else. Depending on the location, age, it can look like just about any other species. So that's where we get down. Acer, when I'm finally done, I probably won't try to, I'm not sure. I have to see if I can tweak the model a little bit more. Because it's only got 55% accuracy, and there you're kind of a coin toss, are you a maple or not. That's not quite right, because you throw it in with all the other probabilities, and there's actually, it's better than that. But it's still not, it's not great. The 66%, I'm fine with that. If you have a true third chance of that being right, I think that's pretty good. So all those other species, I'm happy with that. One thing to note too, we did a comparison to an inventory project that we did of cemeteries in the Milwaukee County area. And what we noticed really quick is what my model missed were all of the dwarf, all of the arborvitaes, like all these little cedars that are small, I'm filtering out because I'm saying only 8 feet or taller. Also, I'm filtering out things that are less than 9 square meters. So for polygons that are too small, you get really weird things, like you get telephone poles and streetlights and things like that when you get these small areas. So those are filtered out. Also, the one thing I hadn't really thought about this early on, but when you have a tiered canopy, which in a contiguous forest, you typically don't have a lot of trees in the understory, like proper trees. You have seedlings and saplings that are waiting for the bigger tree to fall so it can take off. But you don't typically have a real stepped canopy. In parks and cemeteries, though, you do. Because oftentimes you have this edge where you have a big tree and then you'll have other trees, especially in a landscape setting. Landscape architects will plant the big tree and then they'll plant like the dwarf spruce underneath it that kind of create a tiered effect. And that we don't capture that because we're just capturing the tallest tree. So just note that that's a limitation of this. So the outcome, we get a map. Yay, we like maps. But we get a map with the species of all the trees. And going through here, you can see a little bit, it does great on the street trees. That's because that's what it's trained on, right? And that's one downside of this. This model is trained on street trees maintained by cities. And you can see as you get into the yards, like there's a street, this is the backyard area. As you get into there, it's going to start to more likely to call it one of the generic categories, which is one, because the canopies, the trees are a little less distinct, which is part of the reason. And then the other reason is there's a lot of trees in backyards that we didn't model. There's Siberian elms that we don't model. There's a tree of heaven in there that are all these common trees. A lot of them are notorious. They grow up underneath power lines on property boundaries because that person doesn't trim it and that person doesn't trim it, so they grow up into the power lines. It's actually a problem for we energies in this case. But we have this, and we can give an inventory then and count all of the street trees that we have within the community, an area, any extent that we want. We can calculate that out, which we can do with a waffle plot. Well, not just because it's waffles, but I think it's an effective plot. So waffle plot, that's 100%. Each square is at 1%, right? So you can go through and identify what's the composition of street trees in Milwaukee County. You can subdivide this. We can then go in and extract it, take a polygon, throw it in for an aldermanic district, for a school district, for a smaller municipality, whatever you want. All the properties that Walmart owns, that's a small municipality in its own. But so that's one of the take homes is we can give these statistics to various communities. So I noted before the problem with the edges of the boundaries. What I found out at the end of the modeling was that I was predicting trees that were 800 feet tall in Milwaukee County because transmission lines exist, right? And the underlying data from that initial classification, I knew that there'd be errors in it from the edges of buildings, but there was a lot more error, and the error was more pervasive than I had anticipated. So I have to go back and do a step where I'm going to filter out all my polygons using the reflectances, and I did it now. I did a cluster analysis, and you get a really distinct group of these are definitely trees, and these are definitely not trees, but then I have these tails that overlap, and right now I have to come up with a way to try to minimize those tails, so I'm not, at some point I have to draw a line and say, above this you're a tree, and below this you're not. Where I draw that line, I'm either going to keep too many not trees or get rid of too many you are trees to do that. Also, one really funny one is that it caught dormers on houses. Like my house is an old 100-year-old house. It has one roof line, then on the side above the bathroom, it's got the little dormer. Those are seen as trees. And I think it's because the intensities coming back are less. So it's not seeing that as a structure. That's why it was getting misclassified at the beginning, since it's banking off at a different angle inconsistently. But yeah, so we have tens of thousands of dormer trees in Milwaukee County now. I'll get rid of those now. One of the last things here is that I realized that a valuable component of this was not, so this you can't see that well, but these are just all the ash trees. This is West Allis. Where did I grow up? I grew up right there. So you can see all the street trees, see the nice little lines. Does a great job of identifying those. But we can also come up with, because now we carried forward the probability, so not only do we have a prediction that it is an ash tree, we have the probability that it might be an ash tree. So we have, you're 60%, you might be an ash tree. Maybe you're 80% an oak, but you might be an ash tree. Well, this can be really important for forest health reasons. Like when we had an emerald ash borer breakout, you could look, so when we have the next new pest that comes along, and it will come along, we can look and say, this is hitting our hackberry trees. Where do we have the highest densities of hackberry trees? Maybe you go out and you thin some of those areas, so you don't have that high density. So there are ways that we can look at that, or if we know that there's various treatments that we want to do, if we know that there's a tree species that's particularly problematic, we can use this to identify areas that might be have a higher density than other areas of the city. So last part's here. Okay. All right, so lessons learned. The quality of the model is dependent on the quality of the input data. Like this is it. This is everybody's excitement about AI. Everybody's excited about this realistically, just like to point out. 1994, I was a computer science major at Carroll College with an emphasis in AI. AI is not new, large language model. It drives me nuts. But like I'm using random forest modeling, which is artificial intelligence. But in all of this, the quality of the model is dependent on the quality of the input data. You put crap in, you get crap out, right? The size of the data is cumbersome and problematic. Like we have, Milwaukee County had, I think, 1,230 individual LAS tiles, each of which I think were 3 to 5 gigabytes in size. So the state cartographer's office wrote a great script to download those, so I was able to download them all. But then we get goofy things like in this one, some of the tiles are just screwed up. There's bad data on them. They're corrupted in a systematic way. that I would have dug in further if I'm creating the final project, because this is 2020 and I know I'm going to be doing it on a different model. So I said I'm going to pretend those don't exist here. And so we're going to get away from that. Oh yeah, here's just an example of the transmission lines. Sorry, I'm getting too close to this thing. So yeah, we have the transmission lines there, shows that point is, well, yeah, 831 feet above the ground. We got some trucks parked in a lot over there that it's also seeing as trees. So that's just problematic, and that's where I have to go back to the drawing board a little bit. So next steps for me, rerun the model with a better filtering of the lidar data. So that's what I didn't know, that I thought it would be better than that, or more accurate than I should say. We're going to do some additional field validation. So once we get done, we're going to go out randomly sample some of these private land trees and see how much are we getting right, so we have a better sense of the error in the model. We're going to attempt to rerun this for counties that have lower resolutions. Milwaukee County has 30 point per meter. Some counties only have 8 or less right now. So I'm going to rerun it. I'm not quite sure if it's going to work. There's some days I'm like, yeah, sure, this will work just fine. And some of the days it isn't going to work. So we'll see. And then last is to rerun it with the 2025 data inputs and hopefully come up with a process that I can push go on, and then go have a couple beers and come back on Monday. And so yeah, with that, I'll take questions.